Hi, welcome to Lesson 12H, Operations with Vectors in Space.
Pigs in space!
The goal of today's lesson is to effectively apply operations with vectors in space.
Pigs in space!
So this is fairly basic, sort of straightforward type stuff. If, for example, we had some vector and that were a sub x, a sub y, a sub z for the three dimensions, and b were another vector, b sub x, b sub y, and b sub z, then vector a plus b, vector b, would be nothing more than a sub x plus b sub x, a sub y plus b sub y, and a sub z plus b sub z. And that would give us a new vector. We could do the same thing with subtraction. And just take my word for it that it still works. We just take the like components and we subtract them together, just like we did the addition here. If we have some sort of a scalar, if we multiply the vector by a scalar, that's the same as saying this, and then that scalar would then multiply with each of the components of the vector, thus scaling or increasing, depending I guess on the size of the scalar, scaling the vector in each of the components of the same scale. So if we use a little example like this, if we've got some sort of vector here, say we have vector A as, let's say it is 3, negative 2, for example. This is sort of like the matrix form of a column vector. We're more used to seeing it just in a column vector form like that with round brackets, but it is basically a one-dimensional column matrix. So 3, negative 2, starting at the origin, we go across in the x direction 3 units and down 2 units in this particular case. So the vector is like that. And suppose we were to multiply, and suppose k, if we wanted to do k being 2, just to keep things simple, then k multiplied by a would be 2 multiplied by 3, negative 2, which would give you 6, negative 4. And so, again, starting at the origin, we'd then go 1, 2, 3, 4, 5, 6 units in the x direction, and then 1, 2, 3, 4 units down from the x direction, from the x-axis. And notice that the vector hasn't changed direction, it's just changed size. So k being 2, we've multiplied the magnitude by 2. We've scaled the whole magnitude as well as scaling each of the components by 2. So the 3 multiplied by 2 gives 6, and the negative 2 multiplied by 2 gives negative 4. And notice that it's still in the same direction. It's just a longer vector. We could also multiply, say, by a negative value. Let's just say it's negative 1. So k times vector A would be negative 1 multiplied by 3, negative 2. And that would give us negative 3, positive 2. And so if we were to, again, start at the origin and we go negative 3, or so 3 in the negative x direction, we go 1, 2, 3 here, and the positive 2 would be up here. So this vector would be like this. And again, notice now in this case, the vector is still the same magnitude as the original vector here, except that now it's been turned around in the opposite direction. So that's what multiplying by a negative would do. As we've mentioned before in class, that negative just turns the vector around, which it has in this case. Now, one interesting thing about vector operations is one thing we can't do is we can't divide by a vector. And it's a little bit beyond the scope of this course. Because vectors, and I drew this as a matrix, a column matrix here, because vectors are like matrices, in matrix operations there is no division of matrices. What there is, though, is the multiplicative inverse of the matrix. So suppose, for example, we have, actually I'll use a different variable. Let's see, C is some value, is some constant, which is part of the real number system. Then we have some inverse of C, which is the same as 1 over C. Such that if we do C multiplied by C inverse, we get C multiplied by 1 over C, which then just equals 1. Okay, so that's a special sort of property about matrices. So we, instead of dividing, we multiply by the inverse of the constant, which acts as division. So if we were to go back to this example here, if we wanted, say, k were, just keep it simple, 1/2, then k times vector A would be 1/2 multiplied by 3, -2, and that gives us 3/2 and -1. Because to go from here to there, we've got 1/2 multiplied by -2, which is 1/2 multiplied by -2 over 1, because we know -2 is -2 over 1, and we just multiply straight across to get -2 over 2, which simplifies to give you -1. Okay, I know you know that, but that's just how this all works. So it appears as though we've divided by 2, but we've actually multiplied by the reciprocal. So then the vector then, the new scaled vector is 3/2 -1. So we go from the origin in the x direction 3/2, which is half the distance of the 3 units that we went originally in the x direction. So it's about here, which is about 3/2 units. And then we go down 1, and we see that that lands again on the original vector. So it doesn't change the direction of it. It's just half as long as that original vector. So that's about the majority of what we're going to be doing with vectors. We're going to add, we're going to subtract, we're going to multiply by scalars. And so we'll find that vector addition is commutative, so we can add vectors in any order that we like, which I think we've already seen that with the triangle and parallelogram law of vector addition. The associative property holds. So if we were to add 2 vectors together and then add a third vector, that would be the same as adding one of the first 2 vectors with the sum of the second and third vectors. It would give you the same thing. So that's the associative property. The additive identity, if we take a vector and we add the 0 vector, that's going to be the same as the 0 vector added to the original vector, and that just equals the original vector, because adding a 0 to anything just leaves you with the original, even if it's in terms of vectors. The additive inverse, just like we talked about here, but the multiplicative inverse, here the additive inverse, if we add a vector with its inverse, negative, that's going to be the same as adding the negative plus the original, and that's just going to give you the 0 vector. If we want to find the length of k times vector A, then that's going to be equal to the modulus of k, because that's the absolute value of the scalar, multiplied by the magnitude of the vector A. So in this case, when this is a scalar, these brackets here indicate the absolute value, and when it's around a vector, they indicate the magnitude. Okay, and that's going to be the same as, they're going to be parallel to the original vector anyways. And then the last thing is if we have an addition of two vectors and we multiply by a scalar, that's going to be the same as multiplying each vector individually by that scalar and then adding them together, which is the distributive property. So the distributive property holds in vector addition as well. Okay, so those are about all the properties and different operations that we're going to be doing with vectors, vectors in space.
Pigs in space!
And so now we're going to just move along to have some look at some examples tomorrow in class, and then you have a chance to look at these questions, practice questions, in tomorrow in class and be able to finish them hopefully. And in the meantime, after you finish this video, please take a look at some of the examples in the section 12H and get a little bit more insight on these operations. So thanks for watching, and we'll see you in class.